Hello, everybody. Jerry and myself, we're targeting individuals, and basically, Jeremy has got a theory, and the theory is that the TIs that are professing to be able to report that they can record the sound coming in from voice to skull, or known as V2K, can be recorded. And Jeremy's worked very hard to prove that this theory that other people are trying could be wrong. So over to you, Jeremy.
All right. One, it's definitely has a lot of flaws in it. The reason being is, as soon as I hear someone say that they're recording something, or as soon as they mention audio, they're talking about a sound wave, right? Sound is what we normally hear. Sound is what your microphone is recording, right? But there's no sound wave involved with a targeted individual. We are being targeted by an electromagnetic wave or a microwave. And there's a big difference between the two. All right. What is an electromagnetic wave? We can't hear these things, but an electromagnetic wave can penetrate a person's body without causing any discomfort or damage. And what is an electromagnetic wave? It's made up of two components. An electron, and it's all tied in with electricity. This is all part of Maxwell's physics. He's a physicist whose theories are probably as important as, or even more important than Isaac Newton's, but he's not a household name. It's related to atoms, moving electrons, electromagnetic waves, etc. Of just about everything around us. That's Maxwell's physics, which was later expanded on by Tesla. And they've named that car after Tesla, right? Now, what is an electromagnetic wave? An electron has an electric field around it. A cell battery with its positive and negative, your normal cell battery, that has an electric field around it, right? Now, going back to electricity, your electron has an electric field around it. A moving electron or electricity an electron moving from point A to point B has got a magnetic field that propels the electron to the positive, right? Convention takes it that the direction of the current is actually opposite to the direction of the electron flow, but that's physics we'll leave out. So now, an electric current has got both an electric field and a magnetic field, right? Your electron has got an electric field. The moving electron has got a magnetic field. And these two fields are perpendicular to each other. They're also perpendicular to the direction of the electromagnetic wave, right? So to just keep it very simple, an electromagnetic wave, you could probably think of an electromagnetic field as being the ocean, the field, the electromagnetic wave being the wave that travels through the ocean. That'd probably be a better explanation, but that's probably the okay.
Thank you, Jeremy. I just want to say, if you want to show any diagrams, let me know, and what I'll do is I'll pause the video and then and just restart it when you want me to. Okay.
Yeah, all right.
Okay.
Uh,
Thank you.
yeah, probably complicate things too much, but just so I'll just leave it at an electromagnetic wave has got two components to it: an electric field as well as a magnetic field, hence electromagnetic. Now, these things, they're all part of the electromagnetic spectrum, right? Which are
Yeah.
generated by the sun, generated by lights, etc. And all they do is they divide the bandwidths because each has its own properties, right? The longest wavelength, shortest frequency, are the radio waves, which can be several kilometers up to a meter long in wavelength, right? And whatever that converts to in hertz, which is your frequency. Now, a radio wave cannot escape the ionosphere, which is a sphere of charged atoms that just happen to be around planet Earth. They cannot escape that. So radio stations use that in a different way. They bounce the wave off that ionosphere and hence transmit it around the globe. The microwave, which is the next bandwidth down, you got radio, microwave, UV, light, X-ray. I might have got the gamma rays, and they've just divided it up by their wavelength or because of their properties. So you got radio, the next bandwidth down, which runs from about a meter to a millimeter, is called your microwave bandwidth. And that's the one that's used by satellites. Now, this is not to be confused with the microwave oven. Yes, the microwave oven uses an electromagnetic wave which is in that microwave bandwidth. I think it's 2.7 gigahertz. That's the most efficient to do the job. And if you think of how it works, it's working on the water molecule to vibrating, or more correctly, resonating the water molecule and cooking your food inside out. So having that magnetic component is very important because it can be used on the water molecule, which is the dipolar molecule, which I'll come to a little bit later on in the.
Thank you.
All right.
Great.
Now, an electromagnetic wave travels fastest through a vacuum. That's why it's it's an energy within itself, right? You just think of light. Light is part of the electromagnetic spectrum, right? And so it travels fastest through a vacuum, slows down a little bit in air, slows down dramatically when it enters water, right? So that's an electromagnetic wave, which is an energy within, which is probably one of the reasons why it is so efficient to do what it does. A sound wave, on the other hand, which is what we're used to, which is what our ears use, that is a mechanical wave. It needs a medium to travel through.
Do you want me to open the attachment, Jeremy?
Yeah. And I'd suggest that people have that attachment open during this presentation. It'll make it easier to follow.
Right, I'm just going to share the screen now. Right, here we go, Jeremy.
Just scroll down it, and let people have a quick read of it, because
okay. And if anybody wants, sorry, Jeremy, if anybody wants an actual copy of this, if they email, if they email me at re1@protonmail.com, I'll be very happy to to send it on to you. re1@protonmail.com. Okay,
Yeah.
Jeremy?
Alternatively, they should be able to copy and paste it from the chat as well.
Oh, I didn't realise they'd be able to do that if I'm going to be uploading it to YouTube.
Oh, okay. Yeah.
Yeah, so but
But,
they can always email or get a copy.
so it'll be handy to have that open during the presentation because it summarizes what I'm going to be talking about.
Okay.
All right. So going back to a sound wave, sometimes people refer to it as audio. That's a mechanical wave, and that needs a medium to travel through. A lot of people don't realize this, but sound actually travels faster through water than it does through air. Roughly 5 times faster. Now, whenever I hear someone say that they're recording an RF or a radio frequency, in other words, electromagnetic wave, and then picking up as audio, I immediately have concerns because one is how are they identifying the radio frequency that's targeting an individual? That's number one. Number two is it's not like your regular analog wave, which is a continuous wave, which is what our transistor radios convert a radio wave into sound via the speaker. It's not a regular analog wave. The one that's targeting individuals is a different type of waveform, and you're not going to pick up equipment that will translate that radio frequency into a sound wave from an ordinary electronics store. So I immediately have concerns when somebody mixes up the term audio and saying that they're recording voice to skull, because voice to skull is being done with all the activity within the targeted individual's brain, and it's being done with an electromagnetic wave, right? And it's the one I'm going to discuss today is the Lilly wave, which was discovered by Dr. John Cunningham Lilly in 1959 when he first started playing around with dolphins, and he discovered a waveform that was getting responses from the brain's neurons. For example, you mentioned that app in Twitter the other day. Remember that if you could, I couldn't add it, but that app was a load of rubbish that claimed that they could hold an iPhone to a person's head, hotspots, and pick up sound. That was just rubbish. Because your brain's neurons don't go off sound, and with a targeted individual.
I don't believe that was me, Jeremy.
No, you did send that through for me to have a
Oh
look
right.
at.
Oh okay. It was an actual app that could record. I don't remember sending that. But perhaps I did.
So there's a huge difference between an electromagnetic wave and a sound wave. An electromagnetic wave is a lot of people refer to it as an RF or radio frequency that can travel through a vacuum, slows down in air a little bit, slows down dramatically in water. So a sound wave is a mechanical wave which can travel through air, cannot travel through vacuum. It actually travels 5 times faster through water than through air. Now, there are three things you need as background before you can move on to a brief discussion about Lilly wave, which is just a a general overview about what John Cunningham Lilly discovered in 59, right? And one is you need a general awareness of new neural pathways, right?
Right.
Now, our brain neurons are not connected to each other. There's a bit of a gap. What that means is if part of the brain is physically damaged, right? The messages start using other neurons and ends up sending the message onto whichever part of the lobe of the brain for interpreting the information. Now, the first example I'll give is how and why we perceive sound information when underwater. You might want to open that and just have that new neural pathways up.
The Lilly wave.
Yeah.
Yeah, okay.
Right. Now, when we are in normal surrounds, right, a sound wave cannot enter into a person's brain. Why? Because the difference in the mediums are just too different. So a sound wave hits your skull and just bounces off. However, when we're underwater, it's a different matter. You got approximately 100% water outside your body, approximately 74% water within your brain. To a sound wave, it's pretty much the same thing. And we've all experienced this when we've been diving. You perceive sound information. Now, why? Right. So that sound wave, which travels 5 times faster through water than through the air, comes through the water, straight through the thin part of your skull, straight into your brain, which is 74% water. The wave passing through the brain does nothing, right? You don't pick up on it. And actually, a sound wave passing through water, the water doesn't move with the wave. A particle of water bobbles around in a circle, if you like, as the wave passes through it, right? Yet we do pick up sound information with our ears switched off when we're underwater, right? Now, what's happening? That wave is coming through the water, through the thin part of the skull, until it hits the very thick part, the thickest part of the skull bone at the base of the skull. Now the difference is too great. You got the skull about 12–15% water, so it's pretty dense, and that's where the wave stops, and it shakes the skull bone. These vibrations are picked up by nerves, sent on to the appropriate neurons, and then are forwarded on to the temporal lobe, and hence we perceive sound information, right? We actually lose the lower frequencies that we normally hear when we're on land, and we actually pick up the higher frequencies when we're underwater. And there's a reason for this as well. Your frequency is equal to the speed of the wave divided by wavelength, right? That's just a general formula. So that's one example of neural pathways. And the neurophone, which was painted by Dr. Patrick Flanagan, a friend of John Cunningham Lilly, he made a lot of money out of this, works on the same principles. it's not a hearing aid for some people who are partially deaf. Those amplify the sound pressure and people pick it up. This is for people who are completely damaged. And it's something that they place in the ear. It works on the nerves, and when people get used to it, it picks up the sound wave, and that's the neurophone. And so and if you'd like, you could Google and have a look at it sometime. Just for the viewers. So that's one example of new neural pathways. How we perceive sound information when we're underwater with these turned off. The sound wave comes through our brain, 74% water, the base of the skull, and that's where it stops. And then it's transmitted through the brain. Another example of new neural pathways, and with this one I'll draw an analogy, right? If you compare neurons with satellites, right? Of course, the dimensions are very different, but if you imagine a neuron as a satellite. Now, in the Gulf War, 1990-1991, some US military generals did not listen to his scientists. So what they did, they thought it would be a good idea to keep the Iraqi intelligence in the dark by bombing out the satellites over Iraq in that Gulf War. That's in 1990-1991. So they've gone out and they've taken out all the satellites over Iraq, thinking that they'll keep the Iraqi intelligence, the Iraqi generals, in the dark. But then they realized this wasn't working. Why? Because these the Wi-Fi data packets, right? You can think of your Wi-Fi as a little packet of data with a header and footer, so it knows where it's going and it knows where it's been left off. These data packets started using other satellites to transmit the information to the Iraqi intelligence, to home base. And you got to understand that these things travel at the speed of light. To give you a very rough approximation, these things can circumnavigate the globe, the circumference of the Earth, in roughly 8 times in 1 second. So they move pretty quickly. So some US military general thought it'd be a great idea to take out the satellites over Iraq, compare that to a damaged physically damaged part of the brain. However, the messages still got home because the data packets were using different pathways to transmit the information. So I've used an analogy where you can think of the damaged part of the brain, as long as it's not too physically damaged, being the satellites bombed out over Iraq, yet the information got home.
Thank you, Jeremy.
Of course, the dimensions are very, very different, but your brain neurons are not connected to each other. There's a synaptic gap between them. So just a general awareness of new neural pathways is important, because then you sort of gives you a little bit of background knowledge as to why an electromagnetic wave can impact on a TI, because we're not perceiving the information through our ears. This is activity that's happening in our brains. All right, shall we have a break, then cover ions?
Yeah, what I should do then, Jeremy, is I shall stop sharing that for a second, and then I'll pause. Right, over to you, Jeremy.
All right.
Here we go.
Now that's just a very general diagram of the neurons. A neuron doesn't look anything like that. Some neurons have got their nucleus in the center of the neuron, and they're still finding new neurons and classifying them according to function today, as far as I know. But the basic idea is, you see the synapse right in the middle.
Yeah.
There's a gap between the neurons, right? And all right, so that's related to what we were just speaking about before, new neural pathways. You can close it off now.
Okay. Okay, Jeremy.
Now, ions, and why are they important to us? We are not wired, our brain is not wired up with copper wires, right? It's atoms or charged atoms that conduct the electricity within the neurons. The main ones being potassium, which is the atomic number 11, potassium, atomic number 19, and chloride, atomic number 17. The other ones we're interested in are hydrogen, which has got an atomic number of 1, and oxygen, of course, which is atomic number 8. The reason why we're interested in those, the last two, is because that's what makes up water. So now, if I send through a picture of the periodic table, and if you open it up, just open it up and don't move it around, but up to the 4th row,
Right.
the one that I just sent through.
Yeah, I've just had to download it and share the screen. And share screen, and here we go, Jeremy. The 4th row.
All right. If you expand it and just have it showing so that, yeah. If you go up a little bit, sorry, down.
I beg your pardon.
Yeah.
Yeah.
No,
Okay.
No, sorry. If you go up a bit, yeah. That'll do.
Okay.
Now, the periodic table is set out this way for a reason. And if you notice, in the first row, you got 2 elements. In the second row, you got 8, you got 2, and you got 6 on the right-hand side. The third row, you got 2 and 6 again. Now, there's a reason for that. And then in the 4th row, it suddenly jumps to 18 elements, right? Starting from potassium,
19.
which is 19, through to chromium, which is 36.
Krypton.
Krypton. Now, why is that? You got to think of your electron shells or energies, right? There's a general formula, and we're only interested up to the 4th row. There's a general formula for an electron shell, which is 2 times n squared, where n is your electron shell. If you have a look at that first row, 2 times 1 squared is 2. So you got 2 elements, hydrogen, and you got helium. 2 times 1 squared is 2. Your hydrogen atom has got 1 proton and 1 electron circling around it. Then if you go all the way to the right, you got the helium, which has got 2 protons and 2 electrons circling it. Now the helium outer shell is full, right? Now, you look at the next row. 2 times 2 squared gives you 8. And you got, starting from lithium all the way through neon, you got 8 elements there. Then if you have a look at the third row, you got 8 again. Now, why is that? It's because the valence shell or the outermost shell can only contain 8 electrons. There are a couple of elements that can contain 9, but usually it's only 8, right? Now, the other part of the periodic table that we're interested in is why is it arranged in this manner? If you look at the left-handmost column, hydrogen, lithium, sodium, potassium, those elements have only got 1 electron in its outermost shell, right? So 1 out of a possible, in the case of hydrogen, 1 out of a possible 2, lithium, 1 out of a possible 8, sodium, atomic number 11, 1 out of a possible 8, and potassium, 1 out of a possible 8 as well, number 19. Now, these elements or atoms, because they've only got 1 element in its outer shell, they tend to give that electron off, right? Because it's only got 1 electron out of a possible 8 in its outermost shell, so those tend to be willing to give that electron off, in a sense, right? If you move across and have a look at the second last right-handmost column, those so by giving off an electron, they tend to end up as a positive ion, right? Because you got 1 less electron than the number of protons, so it becomes positive. Whereas that second last column on the right-hand side, they've got 7 electrons out of a possible 8 in its outermost shell. So it's only 1 electron short of having a full outer shell. So those tend to want to grab an electron, hence having 1 more electron than the number of protons, leaving them slightly negatively charged. Okay? Some elements from your second left-handmost column and the other column on the right-hand side can become ions, but the ones that are most likely to become ions are that left-handmost column and the second last right-handmost column. Now, why are we interested in these? Our brains are not wired up with copper wire. It's an atom that carries the electron from point A to B whenever there's a voltage spike and a potential difference within a neuron. And which ones are used? Sodium, which is number 11, potassium, number 19, and they combined with chloride, which is number 17.
That's chlorine.
Chlorine. Some people call it chloride.
Oh, okay.
All right. Now, these are the ions or the charged atoms that conduct the electricity within the neurons. If the row on the right-handmost column, they've got full valence shells, or their outermost electron shell is full, and helium, neon, argon, and that row on the right-handmost side, they always remain elements. They never combine with any other atom to become a molecule, right? But the ones we are interested in are that left-handmost column and the second last right-handmost column, namely number 11, number 19 on the left-hand side, and number 17 on the right-hand side. Because sodium chloride forms an ionic bond, which is our common table salt, right? Potassium chloride is a is classed as another salt. And the reason why it combines is because the potassium element has got only one electron in its outermost shell. The chloride wants to share that one electron, so it's got a full outermost shell. So those two combine. So that's just a rough idea about what an ion is. An ion is an atom. It's got to be an atom that has either lost or gained an electron and hence become charged. Now, like I said before, electricity can be conducted in two ways. In our house, we've got copper wiring. Some elements can easily shed their valence electrons in their outermost shell. And copper is very good at doing the job in houses. However, we aren't made up of copper wire. So in the case of brain neurons, it's the atoms that carry the electron from point A to point B. And the ones we're interested in is sodium number 11, potassium number 19 on the left-hand side, and chloride number 17 on the right-hand side. Those are the ions that conduct the electricity within the brain's neurons. As an example, and this is a misconception that a lot of people make, water cannot conduct electricity, right? The water molecule, if you were to have a battery, a lamp, 2 electrodes dipped in water, you pour in distilled water, pure water, nothing happens, right? However, if you were to take some table salt, right, sodium chloride, number 11, number 17, the sodium and the chloride, and if you were to dissolve table salt into water, the light globe suddenly lights up. What's happening? The sodium chloride, the dissolving of sodium chloride in water is the chemical reaction required to break the ionic bond of table salt. And now you got the free atoms floating around in water. So what's happening? The sodium ion is carrying the electron, and so is the chloride atom. And those are the two, and that's when the light globe lights up, and that's when water can conduct electricity. Pure water cannot. However, if you mix some salt in the water, the dissolving of salt in water is the chemical reaction required to break the ionic bonds, and suddenly water does become a carrier of electricity. Right?
Thank you, Jeremy. Yes, wonderful. Bloody hell, to get your head round.
No, it's pretty simple. Might take a couple of times to watch, but it's just a general.
Because for people that are wired like yourself, Jeremy, to this, it would be much easier. And I'm hoping to put this out to the science community, and hopefully we'll get some good answers back, Jeremy.
Yeah, well, it's not that complicated. You just got to think of your electron shells and as to why the atoms in the left-handmost column and the second right-handmost column are likely to become ions and charged atoms. And then you just need to realize that within the brain's neurons, it's number 11 sodium, number 19 potassium on the left-hand side, and chloride number 17 on the second last right-handmost column, that are the atoms that carry the electricity that carry the electron comprising the brain's electricity within our brains, within the brain's neurons. All right. So that's just a general overview of what an ion is and which ones are involved in normal brain function, if you like.
Wonderful. Thank you very much, Jeremy.
And that's covered in that second part of the Word document I sent through. If they'd like, if you want to close it off, and they can have a read of that, and we'll have a break and then come back to discuss why water is so important.
Right, which Word document was that, Jeremy?
Oh, the very first one.
Ah, the lily wave.
Yeah, which is a summary of.
Right, okay. So I'll share the lily wave, and that's oh well, there we go. Yeah.
Yeah, just let them have a read of that, and we'll have a break and come back to.
Okay. Sounds good. So
Right.
yeah, I'm going to stop sharing this for a second, and
Yeah.
then I'm going to pause the video, and then we'll start when we come back. See you in a couple of minutes, Jeremy.
Yeah.
Cheers, mate.
All right. So far we've covered new neural pathways, just a general awareness how it's possible for us to pick up information without using our normal five senses. For example, when we're underwater is one. Physically damaged, as long as the brain isn't too physically damaged, the messages can still get from point A to point B using new neural pathways. And I gave an example of what the US did bombing satellites over Iraq. Ions and where they sit on the periodic table, just to give a view of the general awareness that we're not made up of copper wire. It's the atoms or the charged ions that carry the electron from point A to point B, namely numbers 11 and 19, which are sodium and potassium, which are on the left-hand most column. They've only got one electron in their outer shell. They want to shed that off. And on the second last right-hand column, number 17, second last right-hand most, is chlorine, which is number 17, and that's got 7 out of 8 electrons in its outermost shell, one short of having a full electron shell, so that wants to grab an electron, right? And those are the ones that are involved in the neuron. Now, the next thing that we need the general awareness of is the water molecule and why that is important. So if you open up that
yeah, just downloaded it, Jeremy. I'm just about to open it. So I'll share the screen now. Over to you, Jeremy.
all right. Part of this can be gained from why the periodic table is set up the way it is. But getting to the straight of it, if you make it a bit larger, yeah.
Okay.
Now, the reason why the water molecule is important is because of the way it bonds, right? You got the two hydrogen atoms, H2O, which is water, but the hydrogen atoms bond next to each other as per the diagram. You see H, and they bond with the oxygen atom. Hydrogen has got 1 out of 2 electrons in its outermost shell. It's right at the top of the periodic table. Then you have a look at oxygen, which is in the third last, which is atomic number 8, which means its innermost shell is completely full with 2. Its next shell has got 6 out of 8 electrons. So it's got 2 spaces to fill. So it latches onto the hydrogen atom, and that becomes a fairly solid compound, which is water. But because of the way it bonds, with the two hydrogen atoms next to each other, you've got you've got the electrons. Sure, you've got two spinning around each hydrogen atom, but most of the electrons are spending their time around the oxygen atom. Now, what does that do? It gives the water molecule polarity, and sometimes it's called a dipolar molecule. With most of the electrons spending their time around the oxygen atom, that side becomes slightly negatively charged, and the top of the triangle, where the two hydrogen atoms sit, that side becomes slightly positively charged. Now, why is this important? This gives the magnetic component of an electromagnetic wave something to work with. One example, and something I tried out when I was a kid, when I read up on the water molecule. You can charge an electroscope, right? A glass rod with a bit of silk, you just rub it. I believe that strips electrons. You open a tap, have a trickle of water coming through, hold the electroscope, which is slightly charged near that water, and the water bends. Another way to make an electroscope is a hard rubber rod with wool, and that becomes slightly charged. You hold it against a trickle of water, and the water bends. Now, because water is dipolar, because of its shape, and because the electrons spend most of their time around the oxygen atom, it's got polarity, and that gives the magnetic component of an electromagnetic wave something to work on. Something that we're all familiar with. Just consider your microwave oven. What's happening? It's using an electromagnetic wave to work on the water molecule and cook your food inside out. Why is that possible? Because water is a dipolar molecule. Right? Is that clear enough to understand?
Yes, thank you, Jeremy. Yes.
So just a general awareness of that, and that is what gives an electromagnetic wave something to work on when it penetrates our head. It's working on the water molecule. The magnetic component of an electromagnetic wave is working on the dipolar water molecule. It resonates the water molecules with all the surrounding water molecules resonating at that particular frequency at that point in time. And this resonance of water molecules, which surrounds the brain's neurons, you got to remember, your brain is about 74% water. This has the impact of pushing around the ions or the charged atoms that comprise the electricity within the brain's neurons, and hence the external stimulation. Right? So with the magnetic component working on the water molecule, it causes the water molecules to resonate at that particular frequency, whatever frequency that's been transmitted, which has the flow-on effect of pushing around your sodium number 11, potassium number 19, and chloride number 17 on the periodic table. It's got the flow-on effect of pushing those atoms around, and hence an external stimulation of the brain's neurons. And this can do a number of things to a person. An extremely low frequency can actually kill a person. In one of Barry Trower's interviews, he said, and he's an expert on electromagnetic waves, uh, he states, if you wanted to kill a person and if you weren't in a hurry to do so, you'd use an electromagnetic wave. How long it would take to kill a person, that would depend on the person's health and how heavily that they were targeted by what's commonly called an ELF, or an extremely low frequency, which still sits within that microwave bandwidth. The microwave bandwidth is useful because that's the one that's used with satellites. Your radio wave can't do it, your microwave can. Why is water important? Because of the shape of the molecule, it's got polarity, it's got a positive with the hydrogen atoms, and most of the electrons spending time around the oxygen atom. That part of the triangle becomes negative. All right.
Thank you.
So that's, and the flow-on effect of resonating the water molecule has the flow-on effect of pushing around the atoms, the ions or the charged atoms within the brain's neurons that basically comprise the neurons' electricity, and hence an external stimulation. Is that clear enough?
Yes, thank you, Jeremy.
All right, shall we have a break and then just discuss analog wave and why Lily wave is shaped the way it is?
Yeah, and I'll pause that and wait for us to get back. See you shortly, Jeremy.
Yeah.
Cheers, mate. Right, over to you, Jeremy.
All right, so far we've covered a general overview of new neural pathways. Our neurons aren't connected. We can perceive sound information when underwater. We've explained that. Physically damaged brain, as long as it's not too physically damaged, the messages can still get from point A to point B, because your neurons aren't connected. There's a synaptic gap between them. And there's a lot more to it than that, but we leave that to the neuroscientists. The reason why we covered ions is just to give viewers a general idea that it's actually the atoms, namely potassium 11, sodium 19, sodium 11, potassium 19 on the left-handmost column, chloride 17 on the second last right-handmost column. Those are the charged atoms or ions that conduct the electricity in the brain, and just a rough reason why they become positive and negatively charged atoms. An ion is basically a charged atom, one that's either lost or gained in electrons, sometimes two. But then water is a dipolar molecule. A general understanding of that is important. And we explained with most of the electrons spending their time around the oxygen atom, that side becomes negative. And because of the way it bonds with the two hydrogen atoms next to each other, that side becomes positive. Now that gives an electromagnetic wave, or rather the magnetic component of an electromagnetic wave, something to work with. And the flow-on effect of pushing around or resonating the water molecules with the surrounding water molecules resonating at that same frequency has the flow-on effect of pushing around these charged atoms or ions that carry the electron within the neuron. Essentially, it can change what comprises the neuron's electricity.
Thank you, Jeremy. So
water being a dipolar molecule with the brain comprised of roughly 74% water, that's the molecule that these electromagnetic waves are targeting. It's targeting the water molecule. and resonating the water molecule. Surrounding water molecules resonate at the same frequency, which has the flow-on effect of pushing around the ions or the charged atoms within the brain's neurons, and hence stimulating the neurons, an external stimulation. Right. Do you want to Google an analog wave?
Yeah, sure.
And just put it up on the screen.
An analog wave. So I'm just looking for the best diagram. I'll quickly share the screen here, Jeremy. See if this will do. There we go. Analog wave. Is that good enough?
An analog wave is a continuous wave. That one's a very simple analog wave, right? There can be that's an analog sound wave. And you notice the difference between that's one example of a digital sound wave. That's more to do with your Wi-Fi data, the digital wave, because computers are based around yes, no logic, right? Now, when John Cunningham Lilly started playing around with dolphins in the 50s, he was trying to get a response from, those are all examples of analog waves. The bottom one is a digital wave.
Thank you, Jeremy.
All right. He started off playing around with analog waves, and he did a few other things as well. He used to feed his dolphins LSD, and one of his nicknames was the mad scientist who fed his dolphins LSD. He was trying to get a response from them. Another thing that he used to do LSD trips on himself. And he was a prolific writer and used to write about those trips as well. Anyhow, he started off playing with the analog wave, but he wasn't getting any response from the dolphins, no matter what he did. So if you open up the last diagram.
What, the analog wave, Jeremy?
No, the one I just sent through in the chat, Lilly wave pulses.
Oh, okay, beg your pardon.
This is a very simple diagram of the Lilly wave, just to give you an idea of what's happening.
Right, just coming on to share it now. And there we go.
Yeah. Now, John Cunningham Lilly wasn't getting any results with analog waves. Then, through trial and error, he realized that the brain's neurons required a little time to respond to the stimulation with the electromagnetic wave that he was using on dolphins. So he discovered this particular waveform. If you notice, it's got a positive, then it's got a space of 0, then it's got a negative amplitude. Can you see that on the diagram?
Yeah.
Right. Now, as I said before, by resonating the water molecules, the dipolar water molecules surrounding brain's neurons, that has the flow-on effect of pushing around the sodium, number 11, potassium, number 19, and the chloride, number 17, ions that basically comprise the brain's electricity, right? Now, with this particular waveform, he started getting responses from the dolphins. So what's happening here? With that positive amplitude, that has the effect of pushing around the ions or the charged atoms very quickly in one direction, right? Then that space of zero, it just rests there for a little while. Then you see the negative amplitude. It quickly pushes the ions or charged atoms in the opposite directions. That space of zero being important. Now he started getting responses from the dolphins. So what is this doing? This particular frequency on the screen is targeting the water molecule, resonating the water molecule at that frequency, and having the effect of pushing around, of pushing the ions or the charged atoms very quickly in one direction. Then there's a brief rest, then very quickly pushes them in the other direction, then returns the ions to their original resting place within the neurons. And now he was able to stimulate the brain's neurons. And that's a very simplified diagram of Lilly wave, sometimes called Lilly pulses, which is called a bidirectional biphasic pulse occasionally, because of that space of zero. It's not continuous like an analog wave. It's definitely not a digital wave. But that's the one that the US military spent billions of dollars on. They grabbed the work of John Lilly, took it off him. He had intended it for medical purposes. You know, he was at the time he was with the US Navy and the US National Institute of Health. He had wanted his work to be used to try and cure brain symptoms like Alzheimer's, etc. But of course, US military being what they are, they saw its potential as a mind control weapon and grabbed his work off him, and they turned it into a mind control weapon. Because now they were able to, and this is the one that can do voice to skull, because now they're able to stimulate the neuron and get a response. And that's why it's called Lilly wave, a bidirectional biphasic electric pulse that stimulates the brain and gets a response.
Wow, thank you, Jeremy.
So basically what it's doing is it's targeting the dipolar water molecule. The magnetic component of the electromagnetic field is targeting the water molecule. 74% water in our brain. It resonates the water molecules, like I said, 74% within our brain, resonates the water molecules at that particular frequency, which has the flow-on effect of quickly pushing the ions or the charged atoms that comprise the brain's electricity very quickly in one direction. Then there's a brief rest, then very quickly it pushes them in the opposite direction, and then brings the ions or the charged atoms to their former resting places within the brain neurons. And because he realized this through trial and error, that the neurons required a little bit of time to respond to the stimulation, and hence you've got that horizontal line between or horizontal space between the positive and the negative amplitudes.
Wow.
Now note that Lilly wave pulses may not be the only waveform being used, because as Robert Duncan states, there are 23 ways that V2K can be remotely implanted into the brain. But one would expect that they'd all need to consider what John Lilly discovered, which was that the brains don't respond to a continual stimulation, like say from an analog wave, a continuous wave. It needs a little bit of time to respond. And basically that's what's happening. It's pushing the ions or the charged atoms within the neurons around. And with this particular waveform, which is a very simplistic view of Lilly wave pulses, he started to get responses. And this is what the US military spent billions of dollars on perfecting. Reading a person's thoughts are easy. They already knew how to do that. It's not actually reading a person's thoughts, it's reading a person's brain waves and accurately translating these into images or words or whatever. That part was easy. Why? If you go back to a neuron again, all electric currents have got an electric field and a magnetic field, as I stated at the start. And our brainwave patterns are electromagnetic fields resultant from normal neuronal activity, right? So our brainwave patterns are electromagnetic fields. And these can be translated, and they've got computer algorithms that can interpret these brainwave patterns and throw up an image onto a computer of whatever a person's thinking of or seeing, etc., with accuracy. But to do voice to skull, this is one of the ways to do it, which was discovered by John Cunningham Liddy way back in 1959. But of course, his work was seized, was taken off him and turned into a weapon.
Thank you, Joe. Absolute wickedness in that.
Oh, it's unreal.
Mm.
So basically, that's what's happening. Just your new neural pathways, just to give you a background. Your ions, just to give you an awareness that it's the atoms that carry the electricity within the brain's neurons. Water being a dipolar molecule is important because now the magnetic component of an electromagnetic wave has got something to work on, right? You think of a microwave oven, how does that work? And but these, what we're being targeted with uses very, very little power, much less power than a microwave oven. These aren't designed to cook us. It's just designed to stimulate the brain's neurons. And when they're doing voice to skull, one of the ways to do it is by the consideration of a pulse like Lily wave. And that's the one that was used on the Iraqi soldiers in the 1990-1991 Gulf War, sometimes called the voice of Allah, which got the Iraqi soldiers to drop their weapons and surrender to the Americans.
Wow.
That was their first open use. Of course, to experiment with this, we all know that the US military are using these on citizens today, but way back in the 60s and 70s, when they were perfecting this, they could have picked out any Joe on the street and messed around with him and got this to perfection. Basically, the Lily wave is to enable voice to skull. And that waveform can do it. And the reason why that space is required between the horizontal, between the positive and the negative amplitudes, he found out by trial and error. he wasn't getting any responses from a continuous wave, whichever ones he used. He realized that he realized that the brain's neurons needed a little bit of time to respond to the impacts. And what it's doing is it's pushing around the ions or the charged atoms that are within the brain's neurons, essentially changing what comprises the neuron's electricity.
Thank you, Jeremy.
So that's one part of it. Reading your brainwave patterns it's easy. They already had perfected that. They're simply every single current, especially a DC current or direct current, has got an electric field as well as a magnetic field. They've been able to read these and translate what a person is thinking. The Lily wave can do voice to skull. In addition, there's been a lot of debate where people have been convinced that they've been microchipped. Now, I ran that past Robert Duncan as well, and he said, no, these people aren't chipped. But he said sensors could help the lock-on process. Why? If you think of a neuron again, it's you got the soma, you got the axon, a short electric current travels along the axon. Every electric current has got an electric field as well as a magnetic field, electromagnetic. Now, our brainwave patterns, the resultant electromagnetic fields, are also unique to each person. So now a person can be identified through their unique electricity, which is exactly what they're doing. Like even in the Ukraine war, I was at my uncle's, and he was showing a drone following a Russian soldier. It wasn't using facial recognition, which would be using Wi-Fi data. It was picking up on his unique electricity. And the soldier looks up, sees the drone, and starts running. But he's running back to his camp. And what would have happened once he got to the camp? They would use drones again. They're using drones a lot in this war to bomb that Russian encampment. So the reason why being unique is important. Now, as a simile, I've got two iPhones up, right? Each antenna gives off its own unique, it's got its own unique, what do they call? IP address, right? Your internet protocol address, which is once again an electromagnetic field. The reason why it needs to be unique is the messages sent to this iPhone, they know how to get to this iPhone, and this one's got a different address. So the messages that are sent to this iPhone go to this iPhone. The same as the messages that are sent to my laptop. That's got a different IP address as well, an internet protocol address. One of the reasons why it needs to be different or unique is the correct word. If you had two computers or two devices with exactly the same IP address, I don't know if it's ever happened, they would have picked up on it very quickly. The signal would get confused and would not go anywhere. So that IP address, as far as our Wi-Fi is concerned, and similarly to single out a person, because a person has got their unique brainwave pattern, they can be singled out. And an electromagnetic wave can be sent to them to work on them within their brain. As in, I guess, comparing it to the little Wi-Fi antenna on.
Yeah, that helps it sink in more, because I remember when mobile phones first come out, Jeremy, they used to be able to either clone the chip or the SIM card, so that when the phone rang, it would ring on different phones.
Yeah, I'm not sure.
Some friends of mine had a business, they had an estate agents, and the father and the daughter, they had the same, well, they had the same number somehow, so that the phone would
no. Having the same SIM is a little bit different to having.
Oh no, I know. No, I get where you're coming from, but that just made me twig about having the different same. different SIM cards in different phones and being able to
No, no, no.
phone.
It's not different SIM card. It's the Wi-Fi, the little Wi-Fi antenna.
Yeah, the IP protocol.
Mm.
Yeah. So that's
So
our identity.
yeah. So
You know,
it's
sorry, Joe. No, it's very similar to our identity, isn't it?
yeah.
You know, it's
The same.
unique.
It's unique. The reason why it needs to be unique with regards to electronic devices is if it wasn't unique, the signal would not know where to go.
Yeah.
If you had two,
Unless it was rediverted from the other phone.
no, that's confusing the issue a bit.
Oh no, but yeah, okay. No, sorry. No, all I was saying, it can be redirected.
It can be. Oh, it certainly can be redirected.
Yes.
There's no doubt about it. But to reach the original source from wherever it's been sent, it needs a unique internet protocol address. If these two had the same internet protocol numbers or generated, the signal would go nowhere. So one of the ways to target a person, our brainwave patterns are unique to the person. That's how a person can be. And it takes less than 2 minutes to hone in on a person and grab that brainwave pattern. And once they've got it on their database, they can be tracked anywhere around the wave, anywhere around the globe via satellite.
So do you believe they got that from our DNA?
No, not from our DNA. You hone in on a person, just keep it on. When you start talking DNA, you start starting to talk about biochemistry.
Right.
Just keep it at the basic understanding of electricity.
Yeah.
A brain's neurons, tiny electric current flows down the axon, generates an electromagnetic field. Yeah. Brainwave patterns are resultant electromagnetic fields as a result of all the.
Yeah. No, but where I was coming from, Jeremy, is when they first honed in on me, there would have been somebody that would have had a piece of equipment to hone in on me, or
no,
they would
not required. That can all be done remotely. You just hone in on an area, pick up a person's brainwave patterns, and you've got it. You don't need to have a person beside you with a device. They can hone in on a general area. If you think of Google Maps, which uses digital images, it can hone in on a certain area and pick up an image of your house, for example.
Okay.
So all they need to do is hone in on a general area, pick up that person's brainwave.
Yeah, but how do they know which vibration that person is in the beginning? That's what I'm saying. How do they know? Look, like if there's 50 of us in a room and they want one of you, how would they know which one it was?
They'd probably target a person slightly differently, but once they've got that person's brainwave pattern on their database, you could be in a room with thousands of other people.
They pick you out.
But they'd be targeting you.
Yeah.
Because of your unique brainwave patterns,
Okay.
which are
Jeremy.
resultant electromagnetic fields. So basically, a person doesn't need to be chipped. And if you think of how they can use people around you, that can be done very simply. They just hone into the general area, pick up the brainwave patterns of a work colleague, for example, and target him for a short period of time and used forced speech, for example, and have him or she relating things to you that he shouldn't know. Once they've picked out his or her brainwave pattern as well. So they can do a number of things with these. But just to keep things simple, a person has their unique brainwave pattern, unique electromagnetic field, and that is the easiest and the cheapest way to target someone through their unique. unique electricity. So microchipping is, while it would help the lock-on process and make it more accurate, it would be too expensive. And Frank Allen tried to put forward the argument that a capacitor in a circuit can be a quarter of a millimeter or whatever. I mean, that's really nonsense. Reason why? How are they going to get that chip into a person's head? There's a far easier and cheaper way to do it. You just pick them out by their unique electricity, their unique brainwave pattern, which are, once again, electromagnetic fields resultant from neuronal activity. Because every electric current, even within the brain, has got an electric field and a magnetic field. And as Robert Duncan said, yes, that's the easiest way to do it. They could probably use sensors. I haven't delved into that yet, to help the lock-on process.
So basically, it's just every single human, every person and everything on the whole planet resonates at a different vibration.
No.
All right, not resonates at a different vibration, has a different sort of code, if you like.
Yeah.
You know, exactly different frequency.
A different or a unique electromagnetic field.
Yeah.
Or unique
okay.
brainwave pattern.
Yeah, thanks, James. No, that makes total sense.
Yeah. So everyone's got their unique brainwave pattern, and that's one way to target a person.
Yeah.
When this technology gets expanded, and at the moment they're using brain to computer interface and trying to perfect that, but as Binny Sweeney or whatever from NSA stated, once they've got that perfected, it's just as easy to go from computer to brain interfacing. And once they do that, they'll be able to target whole populations. At this stage, they can't. They can pick out individuals and surrounding individuals for a short period of time, but they can definitely target an individual once they've got that unique brainwave pattern on their database. And this can happen anywhere around the world, because you've got to remember, as an analogy again, our brain can be compared to an iPhone with international roaming continually switched on.
Yeah.
And the only way to stop receiving those messages, in the case of a human,
is die.
Is to put a bullet through your head.
Yeah.
With regards to an iPhone, you can switch it off.
Yeah.
And there's no more electricity.
Oh, okay, yeah.
There's no electricity flowing through the iPhone, so that doesn't receive its messages. You turn the iPhone on again, and then it starts receiving its Wi-Fi data. Yeah, so it's pretty sickening, and this is what they're doing to us. I think that's about it.
Thank you ever so much, Jeremy. That's been amazing. And well, and I'm sure people have been enlightened to it, because what I'm going to do. Yeah, sorry, Jeremy, over to you.
People have been lied to so many times. I mean, when I was on Twitter, when I was following Nils Melzer, a girl was telling me that she was convinced that she's microchipped, and she used to pay $300 or whatever every 3 months to get herself de-chipped, but the voices wouldn't go away. So a lot of misinformation has gone out, and a lot of people have believed that somehow or other they managed to get these chips through the pores of their skull, which is too expensive, too miss and hit, and very unlikely. An easier way to go is through the unique electricity. So because of that information, she's spending $300 every month. The voices don't go away. They've got a conned and saying, they've chipped you. You know, they've chipped you again. And so yeah, so a lot of misinformation, a lot of crap going around, and a lot of TIs whose lives have been so adversely affected that a lot can't even work, are forking out good money just to get some sort of relief. You know, forking out their last few dollars just to get some relief from this
Absolute
psychological
wickedness,
abuse.
isn't it?
It's unreal.
It's been no, because the majority of us we're on benefits or we're
I
struggling
know.
or
I
we've
know.
had everything taken from us or you know and
Exactly.
yeah.
Absolutely. All right.
So,
I hope that
yes.
I'll be
No,
interested.
yeah, well, no, I just want to really say thanks ever so much, Jeremy. I'll let you have the
Mm,
last word, but I want to say that I'm going to put this out to the scientific community and as far wide as I can, so
yeah.
that I'm going to ask for any arguments against what we've discussed, and
Mm,
I'm also going to ask for any comments regarding protection for people that believe that they can hear voices that aren't real and so on and so forth. And especially with the directed energy weapons, if any, because you hear that some of the biggest colleges in the United States are actually um, they're working on stuff like this.
yeah, I
So
know.
yeah, so I'm hoping that somebody within any communities in the world would be able to say, look, guys, we can help. You've got to do this, this, and this, and let's get this
Uh,
stopped. Hey, Jeremy.
I don't think it's that easy, right? Uh, the reason why I said this is for a reason. With Havana syndrome, they're concerned about the diplomats being attacked because it's a security. I don't. Okay, you got David Rubel building shielding devices that might work. He's building something that interrupts that whatever frequency you're being targeted with. You got other people who are building electromagnetic wave absorption materials. That might work because if you think about it, I've got something red here. This has absorbed all the other colors from the light spectrum apart from red and reflects red, right?
Right.
So that might work, uh, absorption material, but how well it would work, I've got my doubts. Another way to disrupt the signal would be to have another wave of a similar frequency or wavelength interrupt with interrupt the frequency that a person is being targeted with, and that's what Rubel is working with. Those might work, but as to their effectiveness, I've got their doubts for the very simple reason that the scientists who created these things, if they knew of a way to effectively shield a person, they'd have devised a way, definitely by now, a way to shield the US diplomats from being targeted. But they haven't. And the targeting of diplomats goes on because they hold confidential information.
So what we basically need is a firewall.
That's getting a bit complex.
Oh
Yeah,
no, but that is how it would be, isn't it? It would need something like that.
yeah. A firewall built into a computer is a bit different.
No, but I
Uh,
mean within us to stop it coming in the first place, Jeremy.
Look, I can't answer that one. Uh,
No,
the only thing I can say is with surety is if there was an effective way of shielding
yeah,
diplomats, the smart ass scientists who created these things,
yeah.
who got PhDs in whatever, they would have devised a way to shield the US diplomats from being targeted. But
Unless
but
they didn't
but
want
they
them
have.
being shielded.
No. I mean, the only reason why the US is concerned about their diplomats is not because of their health. Since when did the US care about any citizen's health? They're only concerned because other countries are now gaining access to confidential information, which diplomats hold, a lot of the public service servants hold. That's what the US is worried about, the security issue. They're not worried about the health of the diplomats. They're just concerned what sort of
Yeah,
information that these
exactly.
guys could have
It's
revealed.
been shared.
And if it was as easy as a firewall or whatever David Rubel's building or absorption materials,
Yeah.
how effective they are, I've got my doubts because some may work.
Everything's hackable anyway, isn't it?
Yeah, don't jump too far ahead though about hackable, because if there was a way, step one, if there was a way to effectively shield, the scientists would have devised a way to shield the diplomats at least. The US government wouldn't be concerned about.
But would they though? Because would a lot of the diplomats even know that these weapons existed?
See, these weapons are such a sinister weapon.
Yeah.
A lot of people who are targeted do not even know it. They don't even know that something's wrong. Like the reason is these directed energy weapons, they implant the message directly into the brain. This is part of the reason. And it beats all the brain's subconscious defense mechanisms, right? Because humans aren't evolved to perceive information directly in the brain. It's not coming through our ears or through our other five sensors. So that's one. The other one is, as long as the person's targeting is only for a short period of time, they might notice something different or something wrong for a short period of time. But then if the targeting stops and only lasts, say, maybe a week or a day, then they'll move on with their life and they'll forget about it. You know?
Yeah, I think that happened. Yeah.
It's when you're being continuously targeted, that's when you definitely pick up on. The UN, when Nils Melzer was there, they did a quick survey. And if you think of the world's population, 7.5 billion roughly, they estimate that up to 4% of the world's population may have at some stage been targeted, right? Like we all know that they can use people around us for a short period of time.
Yeah.
Of that 4%, this is my estimate, maybe 1/25 are definitely targeted individuals. And when I say targeted individuals, they've been under long-term, pretty much constant abuse.
Yeah.
Like you and I.
Yeah.
And that's the only time you pick up, I was being warned about what was going to happen in 1989. In 1991, 1992, I had a job that was going to take me back to Sutherland Smith. I knew something was wrong, but I didn't really think much of it, you know? And I didn't know about these things. I definitely knew about it and experienced voice to skull in 1995, 1996. And that's when they really made a mess of my life.
1980, Jeremy, was when I became the manager of an establishment. And that's when you said about they target you for a short time. Well, they did it to me for about 3 months. And that was the very first time that they ever touched me. That I couldn't even look in the mirror in my car or hold my head up. And they started messing about my eyesight back then, and I'd forgotten all about it. And then all this came, the memories have come flooding back, and I remember it very, very well. you know.
Yeah. One of the reasons why, and that's the most common way that they use these things. I mean, as the UN stated, these things are used to intrude into a person's privacy and sexuality. These are being
Yeah,
used on the LGBT community, sexual conversion.
right.
So-called human enhancement is another term the UN use. These things are being used with threats to publicly shame people.
Yeah, yeah, exactly.
But the most common thing that they've done with all of us, which is so very, very damaging, because when I first definitely experienced this in 1995, when I used to do alcohol rehabs, I used to ask general questions of the psychologists, right? Just to gain information. I knew this was happening. I didn't know anything about directed energy weapons until about 7 or 8 years ago. And they said regression therapy. I used to ask that question, you know. And a lot of psychologists, ethical ones, say they are reluctant to use it on a patient unless it's really, really necessary. Because what normally happens, if you had a really painful memory, the brain tends to repress it, right? So psychologists are reluctant to use it on patients unless they feel it's really necessary because it could be more damaging to their patient. This is an ethical psychologist. Yet, this is what they do to us all the time with no medical supervision at all. And this is the biggest thing that's fucked me up, or what we call it, you know. And all of a sudden, a targeted individual isn't living in 2022 anymore. He's all of a sudden got the 1980s, what happened in 1995, and painful memories that the brain had repressed, as
Exactly.
if it happened yesterday.
Well, what they did to me, Jeremy, is they rewound everything, took me back to the beginning, and it seemed like I'd re-entered my body as a baby, and then I'm learning to live in my body as a man with no brain, no speech, no hearing, no and everything else, and you can't explain that. But
Yeah, well,
well,
one of the most common things that these are used on is that very dangerous practice of regression therapy, where you take a person back through his memories, and
yeah,
if you do it for too long, instead of a person being in 2022, all of a sudden they're living in the
yeah, in
1980s
the
when they should be
past,
living in the
yeah,
present.
agreed.
It's really bad, and this is done without to us without medical supervision.
Yeah. Well, the thing is I think the reason they're doing it without medical supervision is they know they're going to get away with it
They know they can get
because,
away with it.
and not only that, they know that our brains are being uploaded anyway and are being read, so they've got all the data free of charge.
And they can interfere with medical professionals around you, and also they know they can do this with pretty much impunity because they know that they can get away with it,
Exactly.
because
Exactly.
who's gonna believe us unless maybe another TI or maybe a medical professional like Carol Smith, who was deregistered in the early 2000s, a psychiatrist who was releasing papers on this.
Yeah.
Of course, in her case, because she had spoken out of turn, the medical board has turned around and deregistered her and discredited her when she was speaking the
Oh,
truth. When she was absolutely spot on. She'd researched these, and one of the papers that she had was a requirement for a new definition of psychosis in light of the mind invasive technologies that came out of the Cold War. Let me see if I can.
okay, right.
Yeah. and she was publishing papers and helping TIs as well. But of course, because she
What was
spoke
she,
out
a
of tune.
politician, or was she? What was she? Was she a
She
TI herself? Because I don't remember the name.
no, her name's Carol Smith.
Okay.
I'll send that through in the chat.
Okay, mate.
She was a psychiatrist. There are a few psychiatrists around who are helping TIs. If you open up that last one,
Yes,
that's
just
one.
opening it up, mate.
That's one of
Sorry.
her papers. She was a highly respected psychiatrist, a doctor as well as a psychologist. When she started publishing, the medical board shut her down.
Wow.
This is one of the papers that she wrote.
That was 2019 years ago as well.
Yeah, that's right. And then come the UN 17 years later, saying exactly the same thing as Carol Smith, and even more.
Wow.
They've got. So put that through in the chat. All right, Roy.
Yes.
You can stop the recording, I guess. Yeah.
Okay. Well, no,
But
first of all, before we go, Joey, I want to turn around and say thanks very much. And I'll stop the recording now, and I really appreciate everything. But I want to say, because I'm going to put this up on YouTube, and we'd really like as much feedback to everything we've discussed with your theories by anybody and everybody. So, you know, hopefully we could find an answer, Jeremy. Okay?
I'm not sure. I'm not sure if we'll ever get an answer to this, Roy.
No, I don't mean an answer. A reply to the other theory where people are paying to have voices captured as they come in.
That's rubbish. I mean,
exactly. So that's what I was saying. That's why we're doing this video as well, so that the target individual community knows that you've researched this thoroughly. And if anybody has got any arguments as to why or why not, you know, we'd like as many responses within the video, Jeremy, wouldn't we?
And I wouldn't limit it to the scientific community, Roy.
No, physics as well.
I put it out. I put it out to the general community as well.
Oh no, I will do, but I want to get it a little bit further if possible, Jeremy, within the scientific community, because I'd like to see anybody's arguments, and hopefully we might get a couple of whistleblowers that come on that might be able to point us in the right direction.
Oh, I don't know.
Who knows?
Don't know. I mean, basically, all that I've covered is just very, very basic physics, you know, and just a general
Thank you.
And a general idea of how it works, you know.
Yeah.
I haven't gone into anything as complex as what David Rubel was trying to do. I've just tried to keep it as something as simple as to understand for the layperson who doesn't have a background in physics.
No.
Just keep it very simple.
All right. So I'll stop this here then, Jeremy.
Yeah.
I'll just stop the recording. And thanks very much to everybody for watching. I'm going to stop the recording now, and then I'll upload it. And we'd really appreciate your comments, please. And thanks ever so much to Jeremy. You know, because this has taken a lot of research, and really appreciate it.
Not that much research. Jeremy.